Monli, what's linear momentum?
Linear momentum is a vector quantity which is an inertia due to motion.
Inertia due to motion. Okay, thanks.
You're welcome. Daya.
Yes, Monli?
So, do you have any idea what is the components for the linear momentum?
Yes, I do. Hold my chips. So, linear momentum is a product of mass times velocity.
Thank you. No problem.
So, Monli, what is the whole purpose of linear momentum?
Okay, linear momentum gives us the ability to analyze collision and determine the motion of the object after collision.
Oh, collisions. Cool.
Knock knock.
Who is there?
Energy.
Energy. Con permiso. How does energy got to do with momentum?
Well, energy is just like momentum. It can either be created or destroyed, and it's always conserved. So the initial momentum is always equal to the final momentum, and the change of momentum is always equal to 0.
I see. Interesting.
Hey, Monli, did you know that we come across linear momentum all around us? It happens every single day.
Really?
Yeah.
Do you have any examples?
Actually, I have a couple of examples, but just to make it clear, there's two types of linear momentum collisions. There's inelastic collisions and elastic collisions.
Interesting.
So I think I should show you for it to make sense a little bit better.
Okay.
Smart versus S-Class looks pretty much like David versus Goliath. And they will collide to demonstrate their high safety standards. Thanks to its tritium cell, the Smart's passenger compartment remains intact. A hard shell protects the soft core.
Holy guacamole!
I know. That's a perfect example of an inelastic collision because there's physical damage.
I see. And did you see how the car with small mass results a bigger damage than the car with bigger mass?
Yes, that's because the bigger the mass, the bigger the momentum of the object.
Okay, hi class. I'm gonna show you guys a perfect example of the elastic collision. Right now, I'm gonna hit the green ball with the white ball. And you wanna use me a little bit? And before I do it, I have a question for the class. What will happen to the green ball and the white ball after I hit it? Hi guys, good job if you answered that the white ball will stay at rest and the green ball will take off. But do you know why and how does this related to physics? Well, I'm gonna have my little helper right here, their sister, to show me the calculation. Well, this is because of the conservation of momentum. And we all know that the formula for the conservation of momentum is the initial momentum is equal to the final momentum. And we have the data right here. We set up the mass for both balls is equal to 0.17 kilogram, and the initial velocity for the white ball is equal to 0.5 meter per second. And since the green ball is at rest, so the initial velocity for the green ball is 0 meter per second. And we're gonna prove that the white ball is still at rest. Therefore, the white ball, the final velocity for the white ball is equal to 0 meter per second. And that's the formula we're gonna use for this case. So the initial momentum for both objects gonna be equal to the final momentum for the both object. So we just plug in the numbers, and this came out to 0, and this came out to 0, and the calculation right here, and eventually we get the final velocity for the green ball is equal to 0.5 meter per second, which is exactly same as the white ball for in the initial velocity. And this does make sense because of the conservation of the momentum. When the white ball hit the green ball, the momentum of the white ball transferred to the green ball. That's why the green ball take off at the same speed as the white ball. Yeah. Oh my gosh. Mike, are you okay? What are you doing?
I'm trying to challenge myself to spin 10 revolutions without falling down.
Well, come on. I have a little trick that can help you do this. Well,
So, what's this trick?
well, extend your arm outwards instead of holding your arm together while spinning it.
And how's that?
Let me show you. Okay, have your legs do that.
Well, I guess it worked.
6, 7, 8, 9, 10.
So, question for you guys: how did Mike's spinning with his arms extended help him maintain his balance better?
So, Moni, can you please explain to me about your trick and how I was able to balance better when I increased my arm length?
Okay, this is something got to do with physics, and this is called angular momentum. Angular momentum is the amount of rotation of an object that take account into its mass, speed, and shape. Well, the formula we use for calculate the angular momentum would be this. Let me show you here on the board. Angular momentum we take as L, so angular momentum is equal to inertia times omega. It's same thing as mass times radius and times the velocity.
So, what you're trying to tell me is that if I increase my radius, and since momentum's conserved, I would have to decrease my velocity to compensate and conserve momentum, right? So that's why when you increase the radius, you go much slower than you would actually go as if you would put your arms together in your chest. Interesting.
So now that we saw a real life scenario with Mike in the chair, how about we see another real life angular momentum situation like figure skating?
Part of how I start spinning is in my foot. My left foot turns so that I'm no longer moving forward, and the circle I'm skating in is much, much smaller. The other part is where this new equation comes into play. At the beginning, I skate in a large circle so that r is large. Then, when I skate in a smaller circle, r is smaller. Now going back to that equation, because of the law of angular momentum conservation, if r is less, m is constant because your mass doesn't change, and angular momentum is conserved because of the law, then velocity must increase. Now that you know how a spin starts, you might wonder what happens in a spin. Well, the answer to that is quite simple. It's really the same as when you rotate in a jump. So that means that you can increase the speed of the spin because of the moment of inertia and the conservation of angular momentum. Just to clarify, the equation for angular momentum when starting a spin is L equals RmV, and the equation for when you're rotating in a spin or jump is L equals I omega. Next up, change of position and change of foot in a spin. Here you have a combination spin with 3 positions, 2 on one leg and 1 on the other. Did you notice how my speed increased when I went from the first position to the second? Well, that's down to the moment of inertia. In the first position, the distance from the mass to the rotating axis is much greater than in the second position. So that means that the moment of inertia is less in the second position. If the moment of inertia is less, then the angular velocity is greater. Finally, the change of foot. You may also have noticed that my speed increased after I changed feet. Yes, it is also because the distance from the mass to the rotating axis is less, but that's not all. If you look closely, you'll notice that my left leg pushes on the ice while my right toe pick is anchored in one spot. This additional force allows me to increase the speed of my spin.
So guys, now that we have a more clear distinction between angular and linear momentum, how is it that we can tell the difference? How, Monli?
Well, linear momentum is an object moving on a direct path.
Okay.
And angular momentum is an object with angular motion.
Correct. So these both linear and angular momentum calculate the motion of objects, but in their own unique and distinct way. So now we realize that we come across physics all the time around life. You know, figure skating, the rotations of our wheels, car crashes, collisions, pool tables. So it's pretty interesting how physics is all around us and we don't even realize it. So I hope this video helped you guys understand physics as much as it helped us.